So our panelists for today are Rajat Monga, Anima Anantkumar, and Shubho Sengupta. And Shashi Thakur, our moderator, he's from IIT Bombay. He's a VP of Engineering, currently leading many aspects of core Google search. He was here part of our conference last year as well. He was one of the lightning round speakers, and today he's here as a moderator. He has been at Google for more than 10 years, playing leadership roles in web spam fighting, core ranking, universal search, and many other knowledge graph technologies. He has a PhD in computer science from University UT Austin and BTech from IIT Bombay. So without further ado, I'll turn it over to him to talk about artificial intelligence. Thank you.
Thank you. Well, this is going to be, for me, a great learning opportunity as well. This is like artificial intelligence has been in the news pretty much every month. And I think not a month passes by before you hear about AI cracking some previously unsolved cognitive problem, be it machine translation or image tagging or object recognition or path planning or you name it, right? Or even into traditional areas of human expertise such as radiology and image recognition, image scanning and radiological applications. So it's been quite a moment of change, and you've read about it in popular press. New York Times has talked about it. CNN's talked about it. The Google CEO, Sundar, he talks about this moment in time as a transitionary time between where mobile has arrived. Essentially, anybody who can afford a phone has a phone, and a movement into AI first. The world is going into an AI first world. And so it's pretty clearly a pivotal time in technology as well as in product. And it would be great to hear from our panelists. We have a pretty exceptional set of panelists out here who have researched and worked on products based on AI. It would be great to hear from them, their perspectives. And so without further ado, I'm going to start with Anima and introduce her. And then each of them will talk a couple of minutes about their work, about their passions in this area. And we'll then have a discussion and then turn it over to the audience. And I'm sure you have a lot of questions and would love to hear those and have the panel answer those. So Anima here, she's currently a researcher at Amazon Web Services. And she's going to soon be joining Caltech as a chair, as a faculty member in an endowed chair. She has a variety of interests in this space, in optimization and so on. And in tensor algorithms. And she's also got a variety of great awards from Alfred P. Sloan to Google Research Award. And she's a graduate of Cornell and before that, IIT Madras. So Anima, would love to hear your thoughts about this space.
Sure. Thanks, Shashi, and it's a pleasure to be back here. I was here last year at the IIT event, and it's always a pleasure to see familiar faces as well as meet new people. I mean, to me, this is exciting to me amidst this AI revolution. And for me, there are three important ingredients that are responsible for this revolution. One is the set of core algorithms and frameworks that drive artificial intelligence. But the two other important components are data and compute infrastructure. Right? So without access to these very large amounts of annotated data, whether they're coming from customers or whether they're coming from Amazon Mechanical Turk and other crowdsourcing platforms, we would not be able to build these models that are very data hungry. Right? So data is really the key. Without data, there will be no AI. And the other aspect of having large amounts of compute infrastructure is crucial as well. Even back in 60s and 70s, people were attempting to build these neural network models, but where they failed was not having the compute infrastructure. The GPUs and all the modern hardware that enables us to parallelize and have billions of flops of operations per second is very crucial as well. And to me, like, my interest is in developing new AI algorithms that are scalable to these large data sets. To me, modern machine learning algorithms are deep, distributed, and multidimensional. So we are looking at these deep learning models that have hundreds of layers, and being able to have billions of floating point operations, even as a single image is being processed. And depth is crucial to get this, in a way, a multi-scale or a multi-resolution feature extraction from the data. We need distributed learning because we need to have large-scale models that will need hundreds of GPUs to be run on. And the multidimensional nature is what personally is very intriguing to me. Universe lives in multi-dimensions. Our data is multimodal, has relationships in multiple different dimensions. So how do we process and analyze such multidimensional data? My research has been looking at a tensorial way of thinking. So we're all aware of matrices. We've looked at linear algebra, back at IIT. Matrices are good when you're looking at pairwise correlations or linear operators. So if you want to look at higher order relationships and multimodal data, we need tensors. And I've been researching on tensor algebra and how to scale this up and make this practical, and what kind of information can be revealed by looking at these higher order relationships. And now at Amazon, I'm deploying them in a variety of different applications. And our broad goal has been to democratize AI and remove the barrier when it comes to accessing large-scale compute power on the cloud infrastructure and be able to run the state-of-the-art algorithms for a range of applications. So I'll leave it to the other panelists.
Thanks, Anima.
Thanks, Shashi.
So our next panelist is Rajat Monga. He's a graduate of IIT Delhi. He works at Google, is responsible for the TensorFlow team, which many of you might be familiar with. It's an open source machine learning, deep learning library that Google released a couple of years ago. Rajat's responsible for a lot of the work there. He was also a founding member of the Google Brain team. A lot of experience in deep learning. So Rajat, your thoughts?
Thank you, Shashi. Yeah, it's great to be here. Within all the ITs, and a great panel here, really. And talking about artificial intelligence, it's been changing very, very rapidly over the last few years. Over just the last 5-6 years, we've seen things like computers become as good or better in some cases than humans on, say, things like human vision, vision. Additionally, areas like speech recognition, just a few years ago it was really, really hard, and now you use that all the time on your phones and so on. And in putting all of this together, if you think about how vision evolved in case of animals, so the time when vision started to evolve in animals, when they went from just being able to distinguish between light and no light kind of thing to actually seeing stuff, there was a huge explosion in the growth and the diversity of animals. And I think we're starting to see that time here in AI with this change in vision as well. Similarly, with speech recognition, if some of you might remember the days when you still had voice-activated speech menus on the phones. I still shudder to think of those, where I would try to say my social security number 10 times before it would get it, and that was the only way to get it in. Those days are really days of the past now. We can really speak to our phones or assistants, I guess, and not just do these devices and computers understand our speech in terms of just being able to transcribe it. They can also answer us. So combining things like just speech recognition and what Google has been providing for a while in terms of just understanding of that data. I think we are seeing this huge growth in this. Today, if you see, we have lots of assistants now, lots of big companies, including Google, of course. We have an assistant where we're bringing these technologies in a very nice way to the users. These are still early days for the assistants. I think there's still a long way to go. But they do provide us a glimpse of where the future is headed in terms of just making these things easier accessible to our users. I personally am really excited about continuing to push this field forward. There's lots of research still to be done. It's moving very, very rapidly. Every day, every week, we have new research papers that are changing things phenomenally. over the last year. We've seen, we've actually published papers on machine translation, for example, and also included it in products like Google Translate, where you can go from one language to another really, really easily. I've been able to use that personally to communicate with people I just wouldn't be able to without these tools. So personally, I'm very excited about really pushing that research forward. And then the second part is once you have that research, you want to be able to take that and push them into products, bring these technological advances to everyone around us through products. And with TensorFlow, that's an area I'm very, very excited about.
Thanks, Rajat. So our third panelist is Shubho Sengupta. He's a graduate of IIT Kharagpur. He has a lot of background in research in many different parts that led up to this revolution in AI, starting with his work on GPUs for learning back then to more recently work at Baidu in speech recognition. And his current job is at Facebook AI Labs, where he works on various different kinds of AI problems. So Shubho, you want to share some of your thoughts?
Yeah, thank you for having me at this conference. This is my first time, so very good to see a lot of people from the alma mater. Yeah, as Shashi mentioned, I used to work in speech recognition at Baidu's Silicon Valley AI lab, developing essentially firstly doing speech-to-text transcription for multiple languages in both English and Mandarin. The Mandarin models are now essentially deployed in China. It's, as far as I know, the best model for doing these kind of transcriptions. Did a lot of the early work in building the compute infrastructure for doing training at scale. Speech models are actually some of the hardest models you can train along with language. They take like several exaflops to train, which it's a really large number. And in the last 6 months or so, I'd been spending time doing text-to-speech, so doing very natural speech synthesis, leveraging off the fantastic work that came out of DeepMind. This is still a long way to go in synthesis, but we are getting some really, really good results where we get very natural sounding voices. So we live in, as all the panelists have said, we live in very exciting times where the field is moving so fast. There's a lot of progress being made in what I call perception. So if you look at vision, we have gotten really, really good at not only classifying, which is saying what is there in the image, but also drawing bounding boxes and doing like pixel level segmentation where you can kind of basically take the human or a dog or a cat out of the image. And from there, we have done good progress in speech. We have gotten very good at doing what is called near field short utterance, which is what you do when you speak to your phone or any of the assistants like Google Voice, for example. But we're still a long way to go in speech in a very multi-speaker, noisy, far field kind of setting. So speech is, in my opinion, far from solved. Language, we have also made great strides in translation, as Rajat just said. For languages for which we have data, for example, European languages, English, French, German, we have made a lot of progress, but not because I worked in a Chinese company. We haven't made much progress between, say, English and Chinese to English because we just don't have enough data. And the other open question there is not only doing translations that are factual, where you have a news story and you're translating, but also like how do you translate more subtle things like a novel or a fiction, because a lot of subtleties in that. So all the speech and language, there's still, I think, a long way to go, and especially building good dialogue systems, which you can think of as in some way essentially is kind of translation. A question answer is really a translation in some way. So I have joined FAIR, Facebook AI Research, 2 months back, and I'm kind of stepping away from doing perception and moving more and more into planning. So this is doing reinforcement learning, maybe at a large scale, leveraging off essentially games, which is kind of funny because I started my research kind of career working in interactive rendering for games and films. Now I'm kind of going back full circle into using the games as a simulation environment to build intelligent agents. This might sound frivolous that we are working actually on solving StarCraft, which is it's a oldish kind of game, but it's actually very, very hard. One of the interesting things at FAIR is we are like the most blue sky research organization at Facebook. So we don't really have to tailor any of our research to products, which is great to have that kind of independence. So thanks, Facebook. And with that, I'll turn it over to the moderator.
Thanks, Shubho. So for me personally, given my professional work in search, it's like we look at search as a problem of searching over any kind of information, right? And any of these advances, whether it be in language understanding or object recognition or image recognition, at the end of it, it helps us put structure on content, on information, and sort of aids with the search problem and helps us with searching the world and information in particular. So it's really fascinating to have seen all of the progress that all of our panelists described. So I'm going to jump into a few questions we talked about before. Let's see if we can sort of like lift the shroud of some of the complexity behind some of this technology out here. So my first question was like anytime you have some sort of like a pivotal technology, right? Like there's always the hype around it, right? So there was big data. I remember like big data several years ago, and then I used to hear about, okay, the 1,000-person company and their HR records, and people would be selling them big data solutions for 1,000-person companies, right? And it clearly didn't make sense. And now you hear about people talking about this product has AI and that product has AI. Can you help all of us understand like sort of the delineation between simple forms of curve fitting or statistical analysis and the evolution from there into deep cognitive problems and AI? Like what is the conceptual gap between this? And what has advanced? What technically has advanced over the last few years, which has allowed us to solve these harder problems, which are far more than linear regressions and problems of that nature? So Anima, do you want to start with your thoughts on that?
Sure. Yeah, so there's a lot of, I think, buzzwords thrown around. I think back in the 80s, in fact, AI was not the term you wanted to use, right? When there was the AI winter, people then said, OK, I'm doing machine learning, not AI. So the boundaries between these areas is, to me, blurry. But what's important and what we need to distinguish between, say, a company offering AI solutions to a company actually incorporating AI is whether, first of all, a set of hand-engineered or handwritten rules is not AI, right? So the true AI is when it's able to learn structure directly from data and able to use it. In fact, I mean, if you take it even further, should be in an adaptive way and be able to learn as new data come in, right? That's really the ideal setting for AI when there is lots of data and you're able to learn structure from data. So when you were saying it's curve fitting, typically what's done in classical analysis is what are the set of curves you want to fit, right? In the simplest case of a linear regression, you hypothesize that your model is really linear and what are now the weights or the parameters of this linear model. But then by limiting it to a linear model, you could have come up with a very large approximation error. So the world is very highly nonlinear. Now we are trying to approximate it as a linear model. You would pay a high price in terms of approximation error. But then back when the data was less, this made a lot of sense because the number of parameters were few. It was easy to compute the optimal solutions when it came to what are the parameters I need to learn for this linear model. You could solve them, in fact, in closed form. And so back when data was less and compute was less, this was the only thing you could do, right? But the equation changed now when we have lots of data. Constraining it to be a linear model now becomes a really bad approximation error and will give to very bad performance. And now that we also have more compute power, we can afford to build more complicated models. And so for a period of time, the so-called field of kernel methods was popular. And there the idea was instead of doing this analysis in the Euclidean space, I can do it in some other Hilbert space, or essentially change the metric by which I measure the distance between different data points. But again, there we were choosing beforehand what that space was. And so that's where neural networks and deep learning differs, is that you're adaptively learning what are the set of basis functions you want to represent your data in. So in that sense, you're learning what the structure is in the data directly from data itself, rather than imposing it beforehand. And especially in settings such as images or speech or language, where where there's a lot of variability, and it's very hard to come up with parametric models or assumptions that cover all these data points. It's much better to do neural networks, because you're able to learn the set of basis functions to represent them directly from data. And this has been, I think, the key new aspect here. And the other has been now to take this further and say, can we do this adaptively? Reinforcement learning is one of the hardest problems. So now, if we are getting feedback iteratively, can we adapt and be able to come up with mechanisms that optimize some objective function and do the balancing between trying to explore and exploit? And that's where, again, the deep models have shown good promise, because you want to first learn representations and then utilize that to adaptively explore and exploit in different settings.
Thank you. As you speak about Hilbert and Euclid and such, my hair stands up on my hand. I sort of remember Kreyszig. I don't know if you guys know. 3 semesters of Kreyszig.
It all comes back.
Yeah. That's right. Rajat.
So yeah, I think I agree with Anima on some of the things in terms of what we look at, or what we looked at as AI back in the 60s and 70s was very rule-based systems, expert systems. In some ways, too much of a reliance on that was what led us to that AI winter, where it just wasn't feasible to continue to build rules, although there were efforts around that until very, very recently that have recently shut down. I really agree with her also on that. The machine learning parts of it, and maybe that's because that's where I come from, that's where what I see as taking us more towards AI, and of course, the techniques, including deep learning, reinforcement learning, and many others that will combine together to get us to more powerful methods. The things that have changed in the past 5-10 years, I think, that have really helped us get into some of this is data, compute, of course. And that has really allowed us to learn more and more from the data, rather than relying on people specifying the structure, the laws, the rules, just for things like image and speech. Or both of these used to be domain experts who really understood that field would go about and specify what kind of features make sense for images, right? And what kind of features make sense for speech. And even for just structured data that we had in our databases, Anima talked about linear regression and logistic regression and so on. People would basically spend a lot of time really building out the right features to fit into that really simple model that we could live with. And so now with data and compute, we are at this place where we can learn all of that really starting from raw data and not having to worry about putting all this forcing this structure on these problems, basically. Yeah.
So I think I saw this dichotomy between the old world and the new world in Stanford. So I spent 3 years in Stanford statistics, and it's a very classical statistics program. So there was a lot of emphasis on generating parsimonious models, which is like small models, and which has a convex loss function, which basically means there's one minimum. And the emphasis was on that because we only knew how to minimize convex functions. And suddenly there comes an algorithm, which I think is just as important as data and compute, stochastic gradient descent, which we don't really understand yet. And this is a algorithm that can minimize a non-convex function in a 100 million dimensional space, which if you tell any mathematician, they would say, you're on crack. I mean, which really, that's what it is. I mean, we still don't understand how this algorithm works, but it works. And it works in certain domains, especially in perception, where we have very high dimensional signals, as both of the panelists mentioned. So in some sense, I think it's not only the data and the compute that we have, but also kind of finding this goldmine algorithm that nobody really understands how it works. So we tinker around and we figured out how it works, and we get really, really good results. But I should also say that one must be aware of the danger of seeing the whole world as a nail. I mean, there is a place for traditional machine learning. So if you have a data that normal, like logistic regression is still the workhorse algorithm in ranking, and in ranking basically powers ads, which basically pays my salary. It pays the salary of 2 other members on the panel. So don't diss traditional machine learning. There is a place for everything. If you're doing perception, you can use neural nets, but for other things, I think it's a big toolbox.
Yeah, there's like a hierarchy of techniques. You don't want to use neural nets for solving shortest path problems. And then there are problems for which the shape of the problem is already known and you want to tune parameters. You want to use neural nets for like deeper problems than that. Yeah, that makes sense. So talk to us a little bit about sort of like the beauty and intuition that these techniques learn. Like for instance, for me, like a couple of eye-openers where traditionally machine translation used to happen because you used to find parallel corpora, parallel sets of documents, and try to match aligned pieces of text and learn patterns out of that. And then one fine day, sort of there was a leap, and we could learn translation between pairs of languages for which there are no aligned corpora. So there's something deeper going on out here. Or like when the AlphaGo matches were going on and experts were trying to study why a certain move happened, and at some point somebody was talking about, oh, this thing thought like a human, and it had intuition to it. What is this intuition, and how do you think about this when you know what's going on inside this neural net and algorithms behind it? Shubho, you want to start?
Man, that's such a billion-dollar question. I mean, I think it's easier to do in vision because a vision is made of a bunch of convolutional filters, and you can do this, they call it deconvolution. So you can kind of say, oh, the lower levels of the network are learning these edges, and the higher levels of the network or the deeper, the closer you get to the classifier, it's learning, putting these edges together to do like a face or a nose or whatever. That works in vision, but I don't know how to make that work in a normal, so I come from speech or traditional sequence, or not traditional, but sequence to sequence kind of networks, which take a sequence, generate another sequence. I don't really know how to visualize these networks, and I don't think anybody does. And like debugging a neural network is really, really hard. And the only way you get kind of an intuition of how to debug is just run a lot of experiments. It's a very empirical field. I kind of draw the parallel between, you hear about biologists, I don't know, 150 years back, growing these strains of cells, and every day they have to go and look at the strains of cell. This is kind of what we do. We train a lot of networks and get that kind of intuition of what really is happening. For a lot of the networks, you can't really have a good visualization. And this is a very open research topic, that how do you actually visualize in what is happening in the speech network? What is the lower level learning? Is it learning things like phonemes, or is it not learning things like phonemes? Very open. I think it's only kind of solved for vision because we can interpret pictures really well, and we are looking at pictures. For things that we don't have a good visual representation, we can't do much.
So I would like to add a little bit to that. I think as humans, we like to understand things in very simple forms because that's what we can grasp. And that's sort of how machine learning and AI and all of these evolved, because we wanted to map these problems to very, very simple things, whether it's linear regression or whatever, things that we can understand and make sense of. For example, Shubho said stochastic gradient descent is an extremely simple algorithm by itself, but we don't understand it really. And so the tricky bit, and we're seeing this not just in computers or machine learning, but across the board, whether you talk about economics, where we started with very, very simple laws or rules, but we're realizing these are very, very complex systems. And you can't always have a top-down rule that this is how things function. When you put thousands or millions or billions of things together, in this case, cells or neurons, as you might call it in deep learning, and they start to interact in many different ways, and we see these in bees colonies or ants. what emerges is way more complex than what those individual neurons, et cetera, are doing. And it's hard to put a top-down structure because maybe there isn't any. We do want to understand them so we can make more progress in the right directions and we can guide the direction of these fields. And slowly and steadily, we're understanding bits and pieces. Again, like Shiva was saying, we don't understand large parts of how this works. It's largely empirical. But there are very, very specific pieces that we've begun to just understand, like maybe in vision or some parts of speech, or like in the sequence-to-sequence models, we've realized. And again, putting ideas from other fields together, saying, you know what? Why do we want to pick a sentence, really munch that and crunch that, and then generate a new sentence for translating or understanding speech? Why don't we, as we are building this new sentence, actually look at the parts that may be interesting while doing this? And again, with deep learning, people say it's inspired by the brain or works like the brain works. It's, we really don't know. We really don't understand the brain. So yes, it's very, very loosely inspired by that. But again, it's a very complex system that's building bottom up and doing these amazing things together. And slowly, we'll start to understand more of these pieces. But that doesn't necessarily stop us from continuing to move forward and do more amazing things.
Yeah, no, I think all really great points. My research is at the intersection of theory and practice. So for the past few years, I've been trying to understand why non-convex optimization seems to work in these cases. Right? So the classical computer science theory has always been about the worst case. When you say NP hard, it means there exists an instance on which this task is hard to do. But machine learning is all about not solving every instance of the problem, but instances that are more natural or have structure, maybe some lower dimensional representation that we need to learn in this high dimensional space. And so even think intuitively, if you think of the convex function, there is now this nice progress. Like if you just locally make progress, you will move to the globally optimal point. But the problem with non-convex function is there are peaks and valleys and plateaus. And if you see if you ask any practitioner training these networks, and you look at the progress for long periods of time, there is no progress, right? These are called plateaus. And then suddenly there is progress and so on. And so that's why it's still a very trial and error based framework, because, okay, should I wait now and kill this current process and start a new one, or should I, maybe this plateau will suddenly improve and I'll get to a better training accuracy. And so, theoretically, these regions are known as singular regions, or saddle points, or the points which are like a horse saddle. There are directions where you can have improvement, and there are directions where it gets worse, right? So you need to find these directions of improvement quickly, and then you'll be able to quickly move out of it. And so part of my research has shown like how the stochastic gradient descent is better at doing this because of its stochastic nature. Like noise helps, which is very counterintuitive, right? When we think of all other ways, fields of computer science, we try to remove noise, we try to have verification systems, we try to make sure everything works in a very verifiable manner. But that's why machine learning is so different, because counterintuitively, noise will help you get to better points. And in fact, some of the recent research has been showing that it'll help you generalize better. Because intuitively, when you have noise, you have more variability. And on this unseen test data, there, you want to incorporate the variability that's present that you haven't seen so far in your training examples. And so that's been an interesting aspect of now that we are adding noise, can we add that intelligently? Right? So if you think of the Bayesian framework that incorporates these uncertainties, so how do we train these models in an efficient way? That's been our challenge. So that's, I think, one area that we'll see more of, incorporating uncertainty and noise in a more principled manner to help us train models better, faster, and more generalizable. So that's one area, like optimization, that's close to my heart. I think we'll see a lot of progress there. The other is coming to data, right? So unsupervised learning is considered one of the hardest problems, and in research we are making progress, but when you talk to any practitioner, especially in a company, right, the response to that is, oh, what's unsupervised learning? I'll just go label more data. Right, so there's a whole pool of annotators available either internally or through Mechanical Turk. So a lot of industry has been looking at, okay, we'll just get more and more annotated data, or we'll employ that from feedback from customers in many of these consumer-facing applications. But at some point, we'll run out of that, especially in much more complicated tasks that involve multiple modalities. When it comes to video, for instance, hours of video, you can't possibly annotate every single detail of that. And so we'll need to think more about learning representations, but also maybe actively asking only for annotations that will prove to be most useful for training the model. And some of our recent work has shown even these deep learning models, which are typically very data hungry, you can reduce the data requirements by actively looking to annotate only a subset of your samples in an intelligent way, rather than just blindly first taking, getting all the annotations and then training the model. I think that's another area of iterative online learning and adaptive learning. Will see a lot of progress in the coming years.
Thank you. So let's take a couple of, we don't have that much time, and I think I might be between you and lunch. But let's take a couple of audience questions. I'm sure you have questions you wanted to ask the panelists. Go ahead.
Hi. Can you hear me?
Yeah.
Sure. Rajat, it seems AI has still some work to do because you have one O there in your last name and two O's over there. That's just a joke. This morning we heard about education at large being $1 trillion unsolved problem. Any of you can share light on whether you are working on or you are aware of where AI can help in sort of mass customization of education? And now we have smartphones which records a lot of information about us. Maybe that can help guide a person that this is the profession or this is the things you should learn at because you will do good at. So any ideas where AI can help, adaptive learning can help individuals do better and learn what they are meant to be good at? Thank you.
I can take a stab at one part. So the latter part that you said in terms of helping them identify what you're good at, et cetera, that I feel is you could guide the attributes that you're good at, but I would be leery of telling them, what, you should be so-and-so just because of all of these things. That's a slippery slope where you could push individuals down areas where they might actually do much better in other places. It's like a local minima in terms of optimization problems. On the education side itself, I think there's lots of opportunity to just have more customized curriculum, more personalized curriculum, and there are some very, very specific places that do that, including, I believe Khan Academy does that in some ways. I don't know how much machine learning they use. In terms of depending on how well you're doing, it can accelerate the pace or slow it down, et cetera, and give you the right kind of topics to work on and so on.
Yeah, and coming from academia, I can add to that there is a need for, especially as class sizes are growing when it comes to machine learning and other computer science areas. We need more automated, say, grading and automated ways to evaluate in a fair manner. Also, I think we'll see more of cloud-based education. For instance, AWS gives out cloud credits as well as some of the other companies that allow people to now have projects that run on the cloud and quickly they can check the results or they can submit their code online and it gets graded in an automated manner. I think that aspect also will help us scale to much larger audience.
Let's, since we're pretty much out of time, let's actually take maybe 2 more questions, and we'll just have one answer and like a quick version of the answer. So why don't you go ahead?
Okay.
So most of the use cases for AI that one gets to hear about are in speech and vision. And I was wondering if there are use cases around using AI for information management or information curation. So Google, for example, knows about my search history, my bookmarks perhaps, and my photos. Is AI going to revolutionize that to maybe evolve the Google brain, individual, more sophisticated information about individual and help them leverage that? Can you speak to that, please?
Sure. So we are, if you look at Google in different products, including search or Google News, for example, which is a very personalized content curation system, I guess, for you, that's already taking a lot of the things that you mentioned into account. So we are seeing this being included in lots and lots of products, and you'll see more of this over time.
My feeling is you'll increasingly see a move from curated channels, such as curated through people, which is the kind of thing social networks allow you, or curated through your self-subscription to channels, such as what something like Twitter will allow you to do, to machine-curated channels, which are personalized for your interests. I think that's the holy grail there.
Yeah.
OK, one more question.
Hey, guys. So as someone who's working closely in the space of autonomous vehicles, there are 4 problems that you notice quite again and again. One is perception. The other is precision localization. Then you have planning and prediction. So can you tell a little bit more about what you're doing or how things are evolving to help solve those problems?
I think perception is the most far along. And prediction and planning are the really hard ones because both kind of require a model of the world. And computers don't really have a model of the world. For example, I think somebody was saying merging. And merging is a classic example where you can, even before somebody wants to merge, you can see and kind of figure out, oh, this person is going to merge, even before the blinkers are on, because you have this sense of the world. And this is kind of, I think, the next challenge of a lot of these networks. And this is what I'm interested in. And the problem with this is, how do you simulate? And I think the only way forward is maybe game engines in the short term, because going out and collecting test data from a vehicle is super hard. Like, once you get out of a computer, the latencies are super high. You can't move a robotic arm that fast. So yeah, so I don't know, like, these are like super open research problems. So this is why I don't think like automated driving is going to be solved at least in a decade, probably more.
Let's take one last question.
Hi, Mukund Sivaraman, IIT Delhi. My question is in 2 parts, one practical, one philosophical. Practical nature of it is you talked about debugging and neural networks and domain expertise and so on. How do you prevent, I guess, borderline legal issues like racial discrimination when it comes to using AI for mortgage lending kind of practices? So that's the sort of the practical thing. How do you tweak or debug the system? And longer term or more philosophically, I mean, there was a talk by Dilip George. He's working on HTM and neural networks and that's, vicarious. Neural networks are not the ultimate thing, so at some point it's gonna, it's a hammer, it's gonna solve a few problems, but what's next, what's the holy grail is not neural networks, right, for intelligence, it's something else. And are you guys looking into things, or your company's looking into things beyond just neural networks? Obviously you are, but what's next in the search for intelligence?
Regarding the first part, bias in AI and machine learning, this is a huge problem, right? Especially it's like, what kind of training data do we feed in? There was a paper that looked at, the word embeddings are these representations you learn from large amounts of text, and you try to infer the relationship between words. And then what came out of that was that, male was, closer to being the doctor, while female was being closer to the nurse, right? So if you were using this in a downstream task that, say, recommended doctors in your area and somehow was, without being designed for it, but was biasing the system towards these, in terms of race or gender, right? This is a very, hard problem, and it's I mean, it's still an open question. There is this area of causal inference which tries to learn what are the factors that lead, that have causation effects, right? But this is very hard, and in practice, you would need intervention, or you need a lot of additional queries into the system to understand when there are causation effects. So this is still an open area of how we can debias the system, or can we have human feedback? Can we have humans go and test this in different ways and come up with inferences of what the system is doing? Right? To me, the analogy is just as we don't understand the natural world, we are doing a lot of experiments, we're trying to have hypotheses and verifying them. We'll need to do the same with these large AI systems because we don't understand how well they work. And regarding the second part, I mean, ultimately, what is intelligence is very, I think, broad question. To me, anything that's self-organizing and that's able to replicate, that's able to combat against the elements around its environment, right, is intelligent. And that way, neural network can be, it's just a way to organize simpler functions into a much more complex entity, right? And there could be other ways to do the same.
Cool, thank you. So that's pretty much the last question we can take. So let's thank the panelists, and thanks for all the insights you shared.
Thank you. Thank you, Shashi, so much.